Yummy. Thank you. Waves, number 2. What's wrong? Do you have chemistry next?
Yes.
Nice. Electromagnetic waves. Don't relax. Yeah. You got this? Yeah, okay. Okay. So light is a very special type of wave. Okay. It's an example of what's called an electromagnetic wave. So firstly, we all know what light is, okay? And I guess I'm using light as my example of a wave that's called an electromagnetic wave. So you can see light, right? I mean, for example, I can see this light here. Yeah? I can see this light. But I can't see all waves, electromagnetic waves. Light is a special type of wave. It's an example of this type of wave. And in fact, it's the only wave we can see with our eyes. That's electromagnetic. There are other examples. So here are some more examples of electromagnetic waves. So a radio wave, you know, for your radio. Wi-Fi. Now, can you see these waves? No, they're invisible. Mobile phone, X-ray, infrared for a TV remote. Okay, so you want to write something down here. In fact, maybe you should write all of this down. UV? There's loads. Yeah.
Bluetooth is also in there.
Huh?
Bluetooth.
Which one?
The Bluetooth.
Bluetooth, yes, correct. Bluetooth. Yeah, Bluetooth is. I think Bluetooth is almost like a infrared. I'm not sure. Bluetooth, yes. You got those examples? Yeah. So what is rather amazing is all these waves, they're really the same thing. You don't need to write this part down. So what I mean is, although they look very different, okay, your Wi-Fi is very different to light, and that's very different to the wave that's coming from your mobile phone. Although these are very different, they're all actually the same thing. So if they're all the same, how come they're different? Well, what makes them different, what makes the difference between, for example, a radio wave and an X-ray is just the frequency. So the only difference between, let's say this is your TV. Yeah, TV. Old TV. So the only difference between this wave and, say, a wave for your X-ray, you know X-ray? X-ray. The only difference is the frequency. So the X-ray is a higher frequency. That's the only difference. Even though they do very different things, this one you use to watch TV, this one you use in the hospital. The only difference is the frequency. This frequency, I think it's just smaller. Well, it's a lot smaller. Okay, so the only difference is the frequency. That's the only thing that makes them different. You should write this down. In your own words, if you like. I'll give you another example of this idea. So for example, when KJ speaks, that's a sound wave coming out. Yes? And when Amanda speaks, that's a sound wave coming out as well.
And the frequency is different.
The frequencies are different. Amanda's frequency will be bigger than KJ's frequency.
Right.
Does anyone here play any music?
We're not engineers.
Yeah, I didn't think so. Yeah, yes. So her frequency is higher than KJ's. Because her pitch is higher than his.
She speaks quite a
Hmm?
She speaks like quite a
No, but it's not to do with the volume. It's to do with the pitch, which like is with music. You know that do, re, mi, increasing. Nobody plays any music here. Do you really?
Oh, yeah.
Really?
Yeah.
So you know the difference between a low note and a high note?
Yeah.
Yeah? Do you sing? Okay. Do you understand what I'm saying here? No, you don't. Okay. The difference between Amanda, Sohi, and Grace when they speak is their frequency is higher. You seem to know.
Yes, I know.
You sing.
Huh?
You sing sometimes. Yeah. So you understand the difference between something which is high and something which is low.
His voice doesn't help him to sing, I think.
KJ could be a good singer. You don't know this.
I don't think his voice help you. Your voice help you to sing?
Your voice too.
So this is the point I'm making, that the frequency can make the difference, okay? So although they're both sound waves, the frequency can change what it sounds like. And it's the same with the light. If the frequency is bigger, then it will be an X-ray. And if the frequency is smaller, then it will be a radio wave. You get the idea? So just again, if you have, like for example, this could be like for your mobile phone, and then maybe this one here could be for the radio. They're the same type of wave. The only difference is the frequency for this one is bigger. It's faster. It's more cycles per second. That's the only difference. So I have this graph here to show you. So for example, when you have a long wavelength and a low frequency, you have things like radio, microwave, infrared. In the middle is the light we can see. Then if the wavelength is very small, or the frequency is very high, short wavelength, high frequency, then you have things like X-ray and gamma and ultraviolet, UV from the sun. Whoops, sorry.
Visible mean we can see.
We can see it. It's the only one we can see. The rest we can't see. What's interesting also is Wi-Fi. Does anybody know where Wi-Fi would be here on this chart? Wi-Fi. You know Wi-Fi?
No. Yes.
Yes, Wi-Fi. Where would Wi-Fi be?
Short.
Like
Not long.
You would say over here?
X-ray.
Around about here, you think?
Microwave.
Maybe around about here? In fact, it is exactly here. It's the same as microwave.
Never.
Yes, indeed. So if you put your people have Wi-Fi on their?
Everybody.
Everybody.
Now Wi-Fi, you can pick up Wi-Fi.
Yeah.
So you have two signals. You have your Wi-Fi signal and your mobile phone signal. Can someone give me their phone for an example here?
I need a new phone.
I need a good
Bigger
phone.
one.
So, it doesn't matter. Look. Up the top, I can see she has the signal for her phone, Vodafone.
What?
Yeah, and then there's another signal for Wi-Fi.
Yes, right.
Yeah, if you put your phone in the microwave,
Boom.
well, don't turn it on. Yeah. If you put your phone in the microwave and close the door, the Wi-Fi signal goes, but the mobile phone signal stays. And this is because the door blocks microwaves. So the microwave Wi-Fi signal doesn't escape. But the mobile phone signal can still go in and out.
So now when I go back home, when I put the phone in the microwave
Yes.
and give it a call.
You can still call the phone in the microwave, but you can't connect to the internet. To the Wi-Fi, yeah. You can test it. I've done it before. You put the phone in the microwave. You can call it, but you cannot connect to the internet.
Yeah, it's on the
Switch
microwave
off
on.
your cellular data, connect the Wi-Fi, put in the oven and call online like on the Skype or something like this.
Yeah.
No, but if the phone's in the microwave, you have no internet connection.
You will know if it's not ringing.
Oh, but I was just picturing you could just look at the signal bars.
You can see,
Well, yes, if you can't see, then you would have to do something like this. Like, you should be able to call it, but it shouldn't be able to connect. Yeah, it couldn't use the internet. Yeah. So, anyways, we need to put in some numbers now. So, if you can see here, before you write this down, the wavelength for X-ray is very small. That's 10 to the minus 18 meters. And the wavelength for like TV, this is 10 to the 2, 10 to the 2, 10 to the 4. Now you don't have to remember all of this, but the one for the light in the middle here you do. So look, red light has 7 times 10 to the minus 7, and then green light is around about here, and then blue light is down here. You do need to remember this for the exam. You don't need to remember this numbers here, but these numbers here you do need to know. Huh? These are meters because it's length, wavelength. Huh? Oh, shortwave? Shortwave, I think, is for the walkie-talkies, you know, the security people use. Yeah.
Yeah.
Okay, please write this down. The color one is very important. Well, you can just write down red, yellow, greeny, purpley, something like this. There, look, they're the colours of the rainbow. Rainbow, you know rainbow. Red, orange, yellow, green, blue, indigo, violet. You know the rainbow, don't you?
But it's, yeah.
Everybody knows rainbow, I hope. Red, green, blue.
No, it's red, orange.
No. Huh?
The sequence, right?
Sorry. Yeah, sorry. I was thinking of something else. Red, orange, yellow, green, blue, indigo, and violet. Yeah, these are all -7 here.
Red, orange.
Red, orange, yellow, green, blue, indigo, violet. You can just look up rainbow in your native language.
Yeah.
The colours are the same everywhere. So it goes red, orange, yellow, green, blue, indigo, violet. The 7 colours.
It's -7.
-7. Indigo is this colour and violet is this colour. Yeah, I just say purple. That's fine. You can red, orange, yellow, green, blue, purple if you want.
Yes.
Yes, that's fine. purple, yeah.
2,
5 is when the green begins nearly. You know, like 5.25 would be green.
it's like it's changing in every color, in each color in half.
Yeah, well, it's transition slowly, changing from one to the other.
It's a nice way to remember.
Huh?
It's a nice way to remember.
The rainbow is like
Remember the frequency number.
4 to 7.
No, see, for every changing half, like it's changing 7 to 6 here, 6 to 5.
Oh, you mean every 2?
Yeah.
Yeah, it would be about that, wouldn't it? Yeah. Now, in the exam, you're expected to remember these. So the question could then say, wavelength of 6 times 10 to the minus 7 is what colour of light? So you would say yellow. Yeah. So you need to remember this for the exam.
They won't be like too much specific, right?
Now, they usually go for the easy ones, like red, yellow, purple.
Steven,
Yeah.
the second 5 times 10 power minus
Yeah.
7 is pink.
No,
Blue.
red, orange, yellow, green. It's the beginning of blue.
So
It's
it's
like bluey green.
really
Bluey green, yeah. Turquoise, I think, is the name of this colour. Go talk to your art teacher. Alright, can I go on? Yep. Okay, so, you are expected to know these roughly. And what I mean is, in the exam, if you get a very small number, you should say something like, oh, this is probably an X-ray. And if you get a very big number, it should be something like a radio, you know, FM or TV or something like this. So you don't need to remember these, but you need to have an idea of what they are. So for example, you need to know down here is X-rays and UV, and up here is radio and TV. Yeah. Does everybody know what UV is?
Yes, like that's information.
Yeah. Do you know UV, Grace? UV, ultraviolet?
So this can be information.
Oh, the river.
You know it?
No.
the blue one.
Sunblock.
Yeah.
This is UV is what gives you cancer on your skin.
Yeah.
Yeah. So this is a dangerous.
And which one is useful?
Huh?
Which one is useful?
What do you mean?
From the sun, we get from the sun. One is like danger.
Oh, it's dangerous. UV is dangerous. Visible is what you want. UV, you don't want it touching your
There's
skin.
someone who gets in the early morning, which is really useful.
I don't know. I'm not sure. I've not heard this one. Anyway, so go on. So, some properties. Firstly, they're all transverse. These electromagnetic waves are all transverse. So you need to note these. These are 3 properties of these waves. Okay, you got that one? So the electromagnetic waves are always transverse waves. So they're always going like up, down, like this. Yeah? Okay. Now, the next one is rather amazing. That they all have the same speed in a vacuum. So radio, TV, Wi-Fi, X-ray, UV, mobile, they all travel with this speed, 3 times 10 to the 8.
C represents.
It is this speed, it's a constant. I think it's actually 2.999, but we just use 3. Yeah, there's no air, just an empty space. So, the speed of this light or the speed of the wave coming from my phone, they both have the same speed, which is this number. Yes? Okay. And also, there's no need for a medium, which I'll explain now in a minute what that means. Yeah. Okay, let me explain that last one. So for example, if you have somebody talking, this here is a sound wave and it moves in air. Yes? If you put the person in a box here and then put them in another box, no, don't worry, they can breathe in here. But let's say there's no air between the boxes. Do you see what I'm drawing? So what'll happen is when he talks, it stops here. Because there's no air, it can't continue. So you can't hear him.
That's why I can't speak.
Yeah. Like another example, like if you have your ocean wave, okay, you have water, and then here you have land. This wave, it stops here, doesn't it?
Yeah.
Because there's no water here. But light is very interesting because light, there's Earth. No, not that. Light can move in space. Even when this is empty, even when there's nothing here, the wave can still move. So it doesn't need anything to move. It can move in it can move in nothing. It can move in empty space. It doesn't need anything to move.
Can you explain like some bulb like give a lot of light, that's much light,
Yes?
and the other give like only small light.
Oh, this is later.
Oh.
Yeah. Just for now, what's interesting is that the wave can move when the space is empty, in empty space, in a vacuum. It doesn't need anything to move. Yeah, go on.
In normal, you say it's not air.
Yeah.
So the line how to transmit?
The light, when there's no air. So you're saying, like, here, is it? You have a light, and the wave comes out, and there's no air. Yes? Okay. So what's the question?
No, just like you say the example. They have a different example, but the people just stand in the square, no air.
Oh yeah, so there's no air, so that means the sound stays in, but the light can still go in. So the light doesn't need any air, only the sound needs air. So you can see him, but you can't hear him. So you can see him, but not hear. The sound is stopped here because there's no air. But the light doesn't need air. The light can continue. You got the idea? Yeah. Okay. So in the exam, sometimes they ask you for 3 properties. And here are the 3 properties, okay? They're transverse, They move with this speed and they don't need a medium. They can move in empty space. Okay? Yep. All right. Now, because the V always equals the C, then we can say C equals lambda F. Because remember I said C equals V. So, if F is known, then so is lambda. So we can say, and vice versa, we can say lambda equals C over F, or F equals C over lambda. So all I'm doing here, you have this formula, V equals lambda F, but V equals C, so you have C equals lambda F. So you can say lambda equals C over F, or F equals C over lambda. So you always know C. So if you don't know lambda, you can know it if you know the F. And if you don't know the F, you can know it if you know the lambda. So if you know the F, you can know the lambda, and if you know the lambda, you can know the F. So I just wrote that here as well. So if the F is very, very big, what can we say about lambda? Will it be big or small?
Small.
Small. And if the lambda is very big, the F will also be small. And if the lambda is small, the F is big, and if the F is small, the lambda is big. So in other words, a big wavelength means a small frequency, and a big frequency means a small wavelength. They have this opposite relationship. We got this? Yes? Yes? Yeah, that's a problem. Okay, you got this? Yeah. Next. Yeah, me, Grace?
Yeah.
Yes? Yeah. Okay, so before you write this down, don't write it down just yet because I have a picture to explain this. Polarization of light, or any other transverse wave, is when the vibrations are confined to a single plane of the wavefront. So look, the picture will help explain. So what's happening here is the light is moving in all different directions. You see here horizontal and vertical. But when it passes through this, it only moves vertically. So if you look, the light is moving this way, and it's moving this way, and it's moving this way, and it's moving this way. But when it passes through this, it can only the ones moving vertically can go through. So here it's moving many different ways, but only the ones going vertically can pass through. So you're left with just this one. This is called polarization. When you, this process.
What's the material or something?
Material, it's actually, sometimes you have the polarized sunglasses. So it's usually kind of a black material that looks like something you can make sunglasses from. I don't have any, but in fact, you might even have some at home if you have sunglasses. Try your best to draw, if you can try. So the reason for this is to make a nice, clean wave moving in one direction. Try to draw. Got this? Yes? I can go on? Okay. Now you're taking a picture of it, you cheater. Interesting. What's that? Oh, you're writing Chinese. I don't like this. What's all this Chinese here?
I'm just displaying.
Oh no, don't do this. Don't do this.
It's easy to understand, teacher. But if we don't have
Maybe it's easy to understand, but it's not good for your English.
And I don't know what I'm drawing.
Going on.
No.
Yes. Right, so here's our question. What is the frequency of red light? The wavelength is 700 nanometers. I like this picture. I feel like I should put like a little eye here. Like this is eating this or something. Okay. Write this down. Takin, did you write this down? KJ, hang in there. If you got it, okay, let's try it. Okay, so what is the wavelength here? 700 nanometers, was it?
minus 9, right?
Oh no, I gave you the number, did I? What did I say?
No,
Nanometers, yeah.
Nanometer,
Yes.
nanometer.
Great. Come on, get off the QQ or RenRen or whatever it is you're using. 700 nanometers, you're right. So this is 700 times 10 to the minus 9 meters. V equals C, which equals 3 times 10 to the 8 meters per second. So V equals lambda F. That means F equals V over lambda, which will equal 3 times 10 to the 8 over 700 times 10 to the minus 9. So, what's the F here, please?
4.3 into 10,
1.3,
4.3,
4.3
yeah,
times
10,
10 power
14.
14 hertz. So, what is new? This formula you had from the first lesson, true?
Yeah.
The only thing that's really new is when we're talking about electromagnetic waves, you always know this about the speed. Yeah, it's a constant. So this comes from lesson 2, and this one comes from lesson 1. So there's only two formulas. Okay, so write this answer down, please. You got this?
Yeah.
Yep. Okay. So again, just some short questions to do. So they're not, only take you 5 minutes, and we'll finish there. Light, please. Yeah.